Okay, so from last time, we are trying to find the displacement of the particle and also the total distance traveled by the particle. So the displacement, if I started here and finished here, the displacement would be this distance right here. That is why we integrate just straight up. We don't have to worry about signs or anything like that. Just do the integral as is, and it will give us the resulting displacement. But for the total distance traveled, for this, that would be positive, and then as we go backwards, we were treating it as negative, but we need it to also be positive so we can add that distance to the previous distance and get the total distance traveled. So graphically, if this is time on the x-axis and then distance away from where I started, from 0 on the y-axis, then what I have here is motion to the right and then motion to the left. And then technically I would turn around and go back to the right again. So I need to accumulate all this area here to tell me the distance that I went during this time period, but I also need to accumulate this here. I need this to be positive, and that's where the absolute value of the function came in. What that does is it bounces the negative portion, the negative area, into a positive area, so now it's above the x-axis. Okay? So that's what we're trying to do here. In order to do that, algebraically, what we need to do is figure out right there where the graph crosses the x-axis, because then that will give us a starting point, and that's where we finished off last time. Area 1 is already positive, so I can just integrate from 1, the starting point, to whatever this number is right here. It looks like 4, but I don't know for sure, and I can't assume that it is 4. I have to algebraically show that it's 4. And then we're going to say that this is a negative area here. So from whatever this number is, c, to 5, if I integrate this area, I'll wind up with a negative result. So to turn that negative result positive, I subtract that area. The minus, the negative, turns positive, and then I wind up with a positive number here and a positive number here, and I'll be able to combine those two numbers and get my total distance traveled. Okay? So that's like the idea behind what it is that we're doing. So let's see if we can set that up. The first thing we have to do is figure out what this number is so that I can set up these two integrals. In order to do that, I got to find the zeros of the function. So to find the zeros of the function, I set the function equal to 0. And obviously we talked about that last time. But now, to find the zeros, I'm going to have to factor this, which we probably don't know how to do very well, except for to think back to Algebra 2 when we were factoring polynomials that look like this and remembering how to do synthetic division. Yeah, it's not that bad. Now, we have a couple of little hints here. Because we have a graph sitting in front of us, and because we think that the graph crosses the x-axis at 1, we think the graph crosses the x-axis at 5, we kind of have an idea of what our roots already are. Okay? So we can use that kind of idea to help us come up with what roots we should use in our synthetic division. If we don't have a graph, if this was like a test and you were not allowed to use a calculator, then you would not know what the graph looked like. So you would have to do some analysis on the function, meaning you would have to take the derivative of this and then set the derivative equal to 0 to find your critical numbers, so that you could find intervals where the thing is increasing and decreasing. You would have to set this equation equal to 0 so that you could find your zeros, and then you would have to factor it by hand. And then once you had that, you would have a good picture of what this graph is doing. So then you would know that we are positive, we have a positive area in this region and a negative area in this region. That's something that you will have to do if you're not given a calculator. Okay? We are given a calculator, we are given the graph, so we kind of already have a head start. The way to do synthetic division to try to find your zeros is to set up a table. Over here go all your coefficients. So that would be 1 from the t to the third, negative 10 from the t squared, 29 from the t, and then minus 20 here. Remember that you have to include all of the terms, even the ones that are missing. So like if the t squared term was not there, I'd have to include 0 for that t squared term. Every term has to be accounted for. Now what we do is we just start guessing. we say maybe the graph crosses the x-axis at 1, or maybe it crosses at 2, or maybe it crosses at 3, and we just start guessing until we find one. So obviously I'm going to get lucky by guessing 1, because we see that it crosses at 1 here, but that's typically what you do. So with 1, actually let me go with 5, just so that we see some change in numbers. So I'm going to write 5 here, because 5 will work also. The 1 comes down, then 1 times 5 is 5, plus negative 10 is negative 5. Then negative 5 times 5 is negative 25, plus 29 would be positive 4. And then 4 times 5 is 20, plus negative 20, which is 0. So that means that there is no remainder, which means that 5 is a root, which means that x minus 5 is a factor of the polynomial, times the polynomial that's left over, which is, well, it's not x actually, it's t. Sorry. The polynomial left over is t squared minus 5t plus 4. And then this hopefully factors. So now I have t minus 5 times two numbers that multiply to give me 4, but add to give me negative 5. Negative 1 and negative 4. So t minus 1, t minus 4. All of that equals 0. So now I use the zero product property and solve for t, and I get t equals 5, t equals 1, t equals 4. So now I know that my polynomial does cross the x-axis at 1, 4, and 5. Okay? That algebra has to be done before you're able to set up this integral here. You have to show that that actually is 4. And now I have shown that that's 4. So now I can set up that integral. And I'm going to slide this down so I have more room. For part B now, the distance traveled is going to be the integral from 1 to 4, my positive area here, so my polynomial, which I've lost. I guess it's right here, right? T to the third minus 10t squared plus 29t minus 20 dt. So this is like area 1 right here. If I called this area 1, then I could have written the integral from 1 to 4 of area 1 dt, just to show like the concept of what it is that we're doing. Then minus, if I call this area 2, then it would be minus the integral from 4 to 5 of area 2 dt. So that's conceptually what we're doing. Now I'm writing that down. So then minus the integral from 4 to 5 of, still the same polynomial. So t to the third minus 10t squared plus 29t minus 20 dt. All that's left to do now is integrate this thing. And the integral here is going to be the same as the integral here, but the results when we evaluate will be different. And we've already taken the integral already once up above, so we already know what this is going to be. We'll wind up with t to the fourth over 4 minus 10 thirds t to the third, and I'm guessing that's a plus 29t, so that becomes plus 29 halves t squared minus 20t, evaluated from 1 to 4, minus the exact same thing we just wrote down here, so t to the fourth over 4 minus 10 thirds t to the third plus 29 halves t squared minus 20t, evaluated from 4 to 5. We know that we're going to wind up with a negative result in here, but the negative with the minus sign is going to turn it plus, and then we'll be able to add those two together. So let's figure out what this number right here is going to be, and then figure out what this number right here is going to be. T to the fourth divided by 4. So we have 4 to the fourth over 4 minus 10 thirds times 64 plus 16 times 29 halves, so that would be 29 times 8, minus 80. I'm just kind of simplifying as I go. Now that's the first bit. We still have to subtract off that. So minus 1/4 minus 10/3 plus 29 halves minus 20. So all of this is that first integral. Then we have to do the same thing with the second integral. So it's going to be minus 5 to the 4th over 4 minus 10/3 times 125 plus 29 halves times 25 minus 100. Sure, do the easy one. All of that, subtract off exactly what we got right here. So t 4 to the 4th divided by 4 is the same as 4 to the 3rd, which is 64. Minus 10/3 times 64 plus 29 times 8 minus 80. Simplify all that down and we'll have our answer. You did all of this and you got 45/4? Yeah. Okay. Well, we'll see. 45/4 minus negative 7/12 here, and then when we add those together, the minus minus, like we expected, turns to a plus, and we add them together, and we get, what is it, 71? 71/6 is the total distance traveled. So according to this problem, I think we had units on this, didn't we? Yeah, feet per second. So therefore, the total distance traveled is 71/6 feet, which we could approximate to decimal by pressing Control Enter in our calculator, and it would give us probably like close to 12. What is it, 11.83? Okay. I don't know how I just did that in my head. So I want to show you graphing on this. I want to enter in this polynomial. So I give you the polynomial in time. My graph is a function of x, so I have to enter it in as x. So I have x to the 3rd minus 10x squared plus 29x minus 20. Hit enter and I graph it, and of course I get the graph that I'm looking at. Okay? But we've been talking about displacement and distance. So what I'd like to do is actually graph this polynomial, but let's graph it as an absolute value. And that would be the graph of the distance traveled. So instead of what I did, I'm going to bring my function up and make it an absolute value. To do that, down here on the keypad, you have this button that has all your templates on it. And the one that kind of looks like a lol, LOL, that's absolute value of a polynomial template. So I can put the absolute value in there and then type in my polynomial, x to the 3rd, again, minus 10x squared. Oops, don't forget to get out of your exponent before you start typing. Minus 10x squared plus 29x, and then minus 20. Press enter, and notice that it bounces all of those negative portions now above the x-axis, which is really nice because now I can it kind of looks like a bouncing ball, sort of, right? But now I have all positive areas sitting here. So that gives me an idea of what I'm dealing with my distance traveled. Now wouldn't it be nice if the calculator would just go ahead and calculate that area for me? I bet it does too. If I press menu and analyze graph, notice that it has integral on there. Yours does too. Now, I'm not really a big fan of the way that this does this because I can't I can't specifically locate my lower bound and my upper bound, but I can get close. I can get a reasonable estimate here. If I could type in my lower bound and make it exactly 1, and then type in my upper bound and make it exactly 5, then it would give me the exact answer automatically on this. The best I can do, though, is get it close. So I guess I could zoom my graph in so that I can get it really close to 1, but my lower bound would be there and my upper bound would be all the way over here. The best I can do is get it close, and it gives me 11.9. We know the answer was 11.83, okay? That's the exact answer. Well, sort of the exact answer. 11.9 is a reasonably close estimate. And notice that it gave me this nice shaded region, and it makes it look really pretty and stuff. But that's the best that the calculator will do for us here, because we can't specifically enter in the lower and upper bounds on the graph. But on the calculator, it will. So on the calculator screen, what I want to do is press menu. Oops, I'm sorry, I don't want to press menu. I want to press the template button again. And then on that template button, we have all of these options here: fraction, exponent, square root, nth root, blah, blah, blah. But if you notice right there, that's an integral symbol. So it will also allow me to enter in my lower and upper bounds exactly here. So in this particular problem, for my first problem, I just wanted the straight up integral. So I'm going to go ahead and do that. I went from 1 to 5. And then my function, notice that it gives me the option for my function, and then it gives me the option for the variable that I want to integrate with respect to. So I can actually type in t on this one. So I will. T to the third, get out of the exponent, minus t, 10t squared. These calculators are awesome. Uh-huh. You can use them. Okay, so there's my polynomial, dt. And then I press enter, and it gives me the decimal approximation of the actual answer. 10.6 repeating. If I want the fraction answer, the calculator will approximate the fraction as well. So to do that, from here, press menu, and then number, and then you see the option approximate to fraction. And then just press enter, and it gives you your fraction approximation. So 5.3 repeating over, or 5 something repeating over something. It's kind of ridiculous. Or 10.67. But what was our actual answer on this problem? (32/3). So if I were to take whatever the heck that says and reduce it, I mean, I know that 10.6 repeating is 10 2/3, so I can just change it that way. That's an easy one to convert to get 32/3. But that option is there. It seems like it didn't really work out well on this one, but that option is there. So now what I want to do is the exact same thing, except it's distance traveled. So that means I need to include the absolute value notation around that. So to do that, bring up your integral template. We're going from 1 to 5 still. And this time we're taking the absolute value of that polynomial. So bring up the template again and insert the absolute value template. And then type in your polynomial one more time. I'm going to have dreams about this polynomial for how many times I've typed it out. Oops, I accidentally got out of my absolute value thing, so I need to fix that. And then dt, press enter, and it's 11.83 repeating. And if I want the fraction approximation of that, again, number, approximate to fraction, enter. And it does this time give me exactly the 71/6. So you got the right answer, according to the calculator. But now, the catch is, if you're allowed to use a calculator, and you're actually given a function, you can use this. But if you're not allowed to use a calculator, or you're not actually given the function, then you can't. So it's useful to know how to do this in the calculator, but it is not good, it's not wise to rely on it for doing your problems, okay? So you have to understand the concept, because I can give you problems like this that have no function. You have to understand the algebra, because I can give you problems that require you to use the algebra, because you're not allowed to use a calculator. And you also want to know this, because look at how much of a time saver it is. Okay? So if this was given to you as a free response in the calculator portion, absolutely use the calculator. Write stuff down as you go, but use the calculator to do the math.